Welcome to Speaker Night at the David Dunlap Observatory online with the Royal Astronomical Society of Canada, Toronto Centre. My name is Denise Chilton, and I am the RASC Toronto Centre DDO Committee Chair and an operator of the 74-inch telescope here at the David Dunlap Observatory, which is right behind me. Together with our outreach coordinator, Quentin Wayrich, I'm delighted to be your host for tonight's lecture. I'm also very excited to welcome you, our viewers, to tonight's lecture. If you haven't already, please take a moment to say hi in the YouTube chat and tell us where you are joining us from. This helps us make sure that our technology is working properly. The Royal Astronomical Society of Canada's mission is to enhance understanding of and inspire curiosity about the universe through public outreach, education, and support for astronomical research. In partnership with the City of Richmond Hill, RASC hosts outreach activities at the David Dunlap Observatory, or DDO. The observatory is home to Canada's largest optical telescope. We would like to start our evening by acknowledging that the David Dunlap Observatory in Richmond Hill stands on the traditional territories of the Wendat, the Haudenosaunee, and the Anishinaabe peoples, whose presence here continues to this day. We would also like to acknowledge this land is at the meeting place of two treaties, the lands of the Mississaugas of the Credit and those of the First Nations of the Williams Treaty. We thank them and other Indigenous peoples for sharing this land with us. It's my great pleasure now to introduce our speaker for tonight's lecture, Luna Zagorac. Dr. Zagorac is a newly minted postdoctoral researcher at the Perimeter Institute for Theoretical Physics in Waterloo, Ontario. Luna received her Ph.D. from Yale University in 2022, where her dissertation focused on computer simulations and observational signatures of ultralight, or fuzzy, dark matter. When not thinking about things we can't see in the universe, Luna works on mapping ancient Egyptian diagonal star tables to observational astronomical data. Apart from research, she enjoys science communication and writing for astrobytes.org, playing video games, and roller skating. Tonight, Dr. Zagorac's lecture is titled, "What We Can't See in the Universe and Why It Might Be Fuzzy." She examines the stuff we don't see that's shaping our cosmos. If you have questions for our speaker, please post them in the YouTube chat. Luna will have time to take your questions at the end of her talk. Please join me now in welcoming Dr. Luna Zagorac.
All right. Well, hello, everyone, and thank you for being here or wherever you are with me and with us. I'm very delighted to be giving this talk, and I hope you'll enjoy it. So I would like to start off with thanking Quentin Wayrich of the DDO for this fabulous design that he is letting me use as my title slide. I am absolutely in love with what this says about my topic, and I hope you like it as well. And so as we dive in, you will see that the outline of my talk is very much presented in the title, which is sometimes the way it should be, maybe. So the part that isn't specifically mentioned in the title is what we can see in the universe and what we do see in the universe, which is an excellent starting point. And so we'll start with discussing a little bit of the small things, the big things, and the wiggly things that we see in the universe and what those mean to us and how we can infer data from them and connect them to the things we don't see in the universe, which I've just denoted as question mark size things because we don't see them. So we actually have a lot of questions about them, including how big they are, whatever big might mean for each of them. And then finally, why the things we can't see might be fuzzy, or why one of the things that we can't see might be fuzzy. Another way to put this question is, what if some of the smallest things made up some of the biggest things? And I hope that that's intriguing enough that you'll stay with me to talk about that as we get to that part of the talk. But let's start, in honor of the DDO and their optical telescope. Let's start with the things that we can, in fact, see in the universe through, say, telescopes. And so let's start with the big things. So unfortunately, tonight it's pretty overcast, at least where I am, currently coming to you from the Perimeter Institute in Waterloo. And so if you were to go out and look up at the night sky, you'd probably see, clouds and maybe some smog or something like that. So unfortunately, can't do this exercise right now. But on a clear night, if you were near the DDO and you looked up, and maybe there was slightly less light pollution coming from Toronto than normal, you might see something like this. And so all of these shiny things that you would see in the sky, some of these would be stars in our own galaxy. Some of them would be planets, right? So you're often able to see Mars or Venus or some of the bigger planets. And even with a relatively small telescope or even really good binoculars, you can sometimes see even some of the Galilean moons of Jupiter, right? So those are already pretty big things. They're as big or bigger than our planet. That's pretty big for us. And thanks to some new, really big telescopes launched in the sky, like the JWST pictured here, we have really beautiful pictures like this one that show us pictures of sort of newly formed stars and newly forming stars. So this is known as the Carina Nebula. This is sort of a pretty famous photo where you can see a comparison with how JWST did with resolving this image versus how Hubble, say, its predecessor did, and it's really quite breathtaking, I think. And so what we see here are sort of like clouds of gas in the universe. There's a lot of gas floating around in the universe. And if you sort of zoom in on the right piece, you would see baby stars being born. So, like brand spanking new stars. Those are still pretty big things, right? Those are so much bigger than our planet. Um, because I'm a cosmologist, I like things that are really big or really far away. And so for me, my favorite is this image, which shows a bunch of galaxies, right? So there are so many galaxies that you could start to count here. And some of these galaxies, if you sort of stare at the small enough dots of light sufficiently far away, so these are galaxies, that are almost from 13 billion years ago or something like that, which is like a ridiculous sentence, I think. And it's really something that we can see galaxies, even kind of approaching that early. Um, and recently, of course, with the EHT telescope, the Event Horizon Telescope, which is in its own a big thing because it's not one telescope, it's actually a bunch of telescopes all over the world that conspired together, we can now see a picture of our own black hole at the center of our galaxy. So this is the black hole in Sagittarius A. And so we can't really actually see the black hole here. The black hole is here somewhere in the center of this donut, but we can see the gas shaping around our black hole, which I think is really beautiful of the things that you can see in the universe. The gobbling sort of like hungry black hole at the center of our own Milky Way, I think, is a pretty good one. Um, that's not all that we can see. We can also see a bunch of small things. Now, I'm using C a little cheekily here because I think maybe many people in the audience might have heard of electrons, neutrons, and protons before, for instance. So these are subatomic particles. They make up atoms, and atoms, as we know, are famous liars because they make up everything, including me and the desk that I'm sitting on and the, like screen that I'm looking at while I'm speaking to you, and everything like that. Um, so we don't see these, but we know that they're there based on a lot of sort of very, very smart experiments that have been done once, and so we see sort of the effects of these things more than we see them. Um, some particles that you maybe haven't heard of as much or maybe have heard of but maybe aren't covered at some point in high school, or at least they weren't covered in my high school, are things like neutrinos and muons. So these are also particles that we know that exist. They're not particles that we would be surprised to find out there, but it is really interesting to think about where in the universe these are produced. And so here, what this picture in the background is of our South Pole, and you can see the polar lights here. So the South Pole of the Earth. And this is an experiment called the Ice Cube Neutrino Observatory, which is really, really interesting. Because the experiment really isn't up here. The experiment is down here in the ice. So in the ice, people have figured out how to drill these kilometer deep, basically, strings of pearls into the ice, where the pearls here aren't actual pearls. They're actually what's called photomultiplier tubes, which are things that are able to, if there's a little bit of light, they're able to produce a lot of light out of it. And so what happens here is that these are kept perfectly still. And so when a cosmic neutrino, so a neutrino for somewhere out there, in the cosmos, um, runs through this kilometer squared of photomultipliers in ice, you can see lights. You can see these photomultipliers light up because this neutrino is interacting with them. And you can see a muon come out, which is a different type of particle. So you'll never see a neutrino. Or I bet that you've never seen a neutrino in your life, but at this moment, so many of them are going through your body. And sort of the famous thing is that if you have a banana lying around, that banana is showering you in neutrinos right now. It's producing so many neutrinos. So there are all of these small things which maybe we don't, we can't put them in our palm and examine it, but we can't do that with stars and planets either. But we know that they're there because we see the light that they produce when they interact with things. And so finally, I would like to talk about wiggly things, the things that we can't see. These are a little bit different than everything so far, but they're also really, really exciting. So when I say wiggly things here, what I'm talking about are gravitational waves. And gravitational waves are these phenomena in the universe when space-time itself wiggles because something really, really massive happened. And the thing that's really massive that happens that we tend to be able to detect is, say, two black holes merging. So this is sort of illustrated in this GIF of two black holes sort of in spiraling and going to meet each other as they sort of towards the end of the lifetime of this binary of black holes and right before they merge into one bigger black hole. And if you were to sort of plot what this looks like, so this looks a little bit something like this. We have two black holes who are in spiraling together. They get closer and closer, they merge, and then they have a ring down, meaning that it stops being a blob and it starts being sort of like a nice round black hole. And there are experiments, really fantastic experiments, called, say, LIGO and Virgo, that are looking for these gravitational waves and have found some of them starting in 2015. This was a massive, massive breakthrough. And so they look for them like by looking at these sort of waveforms in their signal. And so we will never, even in principle, be able to see gravitational waves because they're sort of ripples in space-time itself. So you'll never notice yourself rippling or the space-time around you rippling. But some really clever communicators have realized that this kind of looks like a sound wave. It's not, but if we transformed it into a sound wave and shifted it by about 400 hertz, we would be able to listen to what a gravitational wave sounds like, or what a merger of these two black holes sounds like. So in this instance, I'm going to play this now. It sounds a little something like this. Yeah, so maybe I'll play that just one more time because it's pretty quick. And so if you hear the whoop at the end, that's what's called the chirp. So that's this part that tells you that the black holes have merged. So not only are we able to see all of these exciting things, we can kind of hear some of them as well, which is really fascinating, I think. Um, but that's not where I make my bread and butter. I make my bread and butter in the things that we can't even in principle see in the universe. And so let's talk about what those are. So of all of the stuff that's out there and of all of the mass or energy that's out there, it's kind of the same to a physicist. Um, we can actually divide it up. So everything that exists, we can divide it up basically into dark energy, which is 70% of all of the mass energy out there, and matter, which is about 30%. Um, the matter so this 30% of everything can then be divided into dark matter and luminous matter, where dark matter is 80% of all of that matter, so 80% of 30% of everything, and luminous matter is 20% approximately, so 20% of 30% of everything. And when I say luminous matter, I mean things like stars and galaxies and dust, some of those beautiful pictures that I showed you on the first slide, but also, me, you, this lamp, this desk, anybody you've ever loved, anything, you've ever seen, essentially. And so What dark energy and dark matter are is a really big question, and it's most of the stuff that's out there, but it's not stuff that we can see. I have no idea what dark energy is. That is not the topic of this talk, though many wonderful people work on it, and I'm sure can give excellent talks on it maybe in the future. What I'm really interested in is what this dark matter is. And so just as a joke, xkct.com are excellent comics that have a lot of jokes about dark matter and dark energy. They, I think, explain them kind of nicely. So this one is, like when you buy 2% milk, it's 2% milk fat. But whole milk is not 100% milk fat, of course, because gross. Who wants to drink 100% milk fat? It's 3.5. And so the question is, okay, so what's the rest of it? And about 27% is dark matter, and the remainder is dark energy. It's okay if you're not laughing, but I laughed. So props to Randall Munro and his comics. We'll see a few more. So, okay, I'm telling you that this dark matter is really interesting. We can't see it. There's a lot of it. But a very reasonable question to ask is then, okay, well, if we can't see it, how do we know that it's there, right? If we can't detect it directly, how do we know that it's there and I'm not just pulling your leg? Which is a good question. So historically, it started from a French term called matière obscure, or obscure matter, if you like, but it's sort of morphed into dark matter. Dark matter is actually kind of a bad term for it because it's not necessarily dark; it's more transparent. It just doesn't interact with light. And so the reason that we suspect it's there is that we can map how galaxies move, how galaxies sort of rotate around their center the same way that the Earth rotates around its center, around its axis, rather. And so if you sort of count up all of the light that there is, you can get a number of how much mass we expect there is. But also, if you know how it's moving, we know how much mass we expect there to be for it to move that fast, because mass and gravity are the things that make things move in space, right? That's the fundamental thing. And so just from the visible disk, right, just from like this, something that looks like this, we expect this type of movement down here, but actually it's moving like this. And so there's this big gap, and this big gap is sort of this question of missing mass in the universe. We know that there has to be mass there, or something is weird with gravity there, or something like that. But we don't know what it is. And so that is what we refer to as dark matter. Now, that begs the question, okay, so where does dark matter live in the universe? Is this dark matter in the room with us right now, Luna? And the answer is maybe. So if this is our Milky Way, this is, of course, an artist's image of a galaxy. It's not actually our Milky Way. But if this were our Milky Way looking something like this, we would be living around here. And the dark matter halo would be totally surrounding our galaxy. So whereas galaxies are sort of like pancakes, right? They're sort of flat disks. Dark matter halos are sort of these spheres full of dark matter that surround them, whatever this dark matter may be. So in the center, we have this regular matter or luminous matter. Cosmologists sometimes refer to it as baryons. This makes particle physicists angry because they think of baryons as something else, but such is life. And surrounded by it is the dark matter halo, which is sort of the object that I'm really interested in studying and what this is made of. And so there are many ways to just make a blob of mass, right? All that this gray here is just some mass coming from some question mark size thing that doesn't interact with light. And so that could be a variety of things. So where the mass is coming from, that's the 10 million Swedish krona question, which is of course the prize you get for winning the Nobel Prize. That's the money that comes with the Nobel Prize. And so this is another XKCD comic that kind of plots here from 10 to the 30th kilograms. So that's about the mass of our sun. 10 to the 24th kilograms, that's about the mass of our Earth. Like somewhere on the order of 100 kilograms, that's us. And then all the way down into, scales where like electrons live and stuff like that. So scale of an electron, there are all of these different sort of theories of what dark matter could be. So dark matter could be like enormous black holes that we forgot to account for that live somewhere, or, in the center of the galaxy, or at least partially maybe. They could be new particles that we haven't thought of yet. They could be a lot of stuff. Here, of course, there are a lot of jokes. So axions are a real theory, and we'll talk about them a lot today, actually. Um, pollen, bees, 8 balls, and no-see-ums are probably not real theories, though I wouldn't put it past physicists to name something. Something like that. But so there's a lot of space to explore, right? It could be a few very massive things that are making up this halo, or it could be so many very light things. And right now, we just don't know. One caveat to this that is important to keep in mind is that we know we know that something is wrong based on our current understanding of gravity. It is possible that our understanding of gravity is wrong, that we're not actually missing mass, we're missing a better equation for gravity. And people do work on this. This is still a very open question, and it's an interesting question. Um, However, while it's not ruled out as an idea, it's not super favored either. So this is still an option, but there's no sort of smoking gun evidence that we've all been fooled and this is the way that we should all be looking. So there are still plenty of exciting ideas out there to think about. Um, Okay, so with that, with this massive clump of things, or maybe wrong equations of gravity in the universe, we'll move on to the question that got me the title of doctor, which is excuse me, which is, could dark matter be fuzzy? And so to ask whether dark matter could be fuzzy, the first question is, well, what is fuzzy dark matter? What does that mean? So, fuzzy dark matter is one theory. So, it's something that we are working on. It's not, we don't know that this is the right answer, but we don't know yet that this is the wrong answer. So, it's still worth thinking about. And so, it's made up of particles called axions. Remember, I mentioned those a second ago. They were on that XKCD comic. And these axions are a very general theory of particle that may or may not exist. And they can have a lot of different masses. Fuzzy dark matter specifically has a very, very low mass. The mass is so low that we don't quote it in kilograms or grams or nanograms or picograms. We quote it in electron volts, which means that it's so low that only particle physicists and particle cosmologists care. So, for reference, my particle has a mass that's on the order of 10 to the minus 22 electron volts. Um, Whereas an electron is like 500 kilo electron volts or something like that. In other words, excuse me, comparing the mass of the particle that I study to a mass of the electron is equivalent to comparing the mass of the electron to the mass of a tennis ball. So it's incredibly, incredibly small. So in this scenario, that dark matter halo is made up of so many of these tiny axions. And furthermore, axions are a type of particle called a boson. You don't need to know a lot about bosons, but you have to know that bosons are particles that like to cluster. They're not like electrons, which are sort of, they're fermions, they're individuals, they like their space. Bosons really like to be together, as densely packed as possible, which will come into play. So what that means is that if we look at what a cross-section kind of in density of a fuzzy dark matter halo looks like, where here is sort of the center of the galaxy to the left and to the right is sort of far away from the center of the galaxy, the density behaves a little bit differently than in what's known as cold dark matter, which is sort of like a generic dark matter idea that we sometimes use as cosmologists. You sort of assume the minimum number of things, you assume that it's some particle, and then it's cold, meaning that it doesn't move at relativistic speeds, because we know that dark matter moving at relativistic speeds would make it hard to form galaxies, basically. And so cold dark matter has this behavior that's sort of very similar to fuzzy dark matter on the outside, but on the inside, you see this what's called a cusp. So it seems like the density is going to infinity in the center, which is not very nice and not very astrophysical. We don't like that. However, fuzzy dark matter, because it's made up of these bosons that really like to clump together, has what's called a core. So there's this bump where all of these particles are sort of, fighting in one big snuggle pile to be as close to the center of the galaxy, and naturally form this core. So that's one of the reasons why we first started liking fuzzy dark matter as an idea, especially since when you go out far enough into this region that we know as the skirt, as compared to the core, which is sometimes called the soliton. So the skirt looks very much like cold dark matter. which is good because cold dark matter does pretty well when considering sort of the large scale picture of many, many galaxies. It's really only that when we zoom into the very center of the galaxy that we become, unhappy with it. And so this is sort of a schematic of what the cross section of a fuzzy dark matter halo looks like. So let's look at what a fuzzy dark matter halo might actually look like sort of visually. So if you're like me, your brain immediately produced something like this, which is a perfectly spherical black cat with a little galaxy at the center. That is, of course, not what they look like, sadly. What they look like is a little something like this. So here I'm showing you two blobs of these axions that are sort of merging together. And they form this, which is a fuzzy dark matter halo. So let's watch that again one time. So these two blobs by themselves are not halos, but once they merge, they form something that might be a halo. So this might host a galaxy at the center that looks a little bit something like ours. And the two main things to notice in this still from this GIF that I made using my simulation code that I use for research. So two things to notice is the central region. See how there's sort of like an egg-shaped, very yellowy thing? That's the core. And also to notice that the core is sort of moving around. It's sort of being extended in one direction versus another, and it's sort of like getting wider and narrower, right? So it's sort of dancing around this core. And also notice sort of all of these snaky bits. So darker is less dense here, lighter is more dense. And so this sort of these patterns that we see, this is what's called the fuzziness. This is what we refer to as the fuzziness of dark matter. And so the two things that are different about a fuzzy dark matter halo over a cold dark matter halo are the core and the fuzziness out here. Right. So you will remember that I told you that, or you might remember that I told you that this halo is made up of axions, so super super tiny particles, much tinier than an electron. And so what that means is that they're tiny enough for us to kind of treat them like an electron, by which I mean to think about them almost quantum mechanically. So that begs the question: how is this fuzzy halo like a hydrogen atom? So, if we're looking at an electron in a hydrogen atom, you may or may not remember, but a hydrogen atom is the simplest atom that you can make. So, it just has one proton in the center and one electron circling it, right? And so, about 100, 120 years ago, some people thought very hard about this model of the electron. I came up with a few wrong things before we got to what we believe is the right thing. And so you might have seen these in school or in other talks, maybe. There are these sort of electron orbitals, which is where on average the electron likes to live given some energy. So if sort of the electron is at its lowest energy, it lives somewhere in this sphere where we assume that the proton is in the center. If it has slightly higher energy and angular momentum, it sort of likes to live in this on these two spheres. And then if it has even higher, it can live on these sort of like quadrupole moment, what it's called, etc. A similar thing happens with a fuzzy halo. The difference is that we don't have one particle making up our fuzzy dark matter halo. We have so many that it's like not even worth counting. But we sort of see similar behavior in the halo. Is my GIF going to play? Okay, my GIF is not going to play. It played in the practice round, so I apologize for that. But we see these shapes that are very similar between these electron orbitals and this sort of behavior that we see in the fuzzy dark matter halo. So if this were playing, what you would see is that this leftmost bit would be going kind of like in and out. This is sometimes called the breathing mode. And if you looked very closely at the core of the sort of pink and purple halo that I showed you, that like yellow core in the center, you would have seen that it kind of like goes in and out. It gets a little bit denser and then it relaxes a little bit. And so this is something that this is an effect that we can see and that we can isolate very precisely using sort of the same ideas in quantum mechanics as the hydrogen atom and the electron, which is pretty cool. Similar thing happens here, where if this were playing, you would be seeing the center go left and right, sort of similar as the electron bouncing between these two poles. And again, here you would be seeing this sort of like square moment of sort of going like across and then a plus. So a fuzzy halo, despite being so many times larger than an electron, right? An electron is one of the tiniest things that we can imagine. And a dark matter halo, like a whole galaxy and all of the stuff around it that's even bigger than the galaxy that we don't see, that's some of the biggest things that we can imagine. So some of the smallest things that we've ever proposed make up some of the biggest things. And so we can treat astrophysics with the same ideas as quantum mechanics, which I think is very cool and somewhat unexpected. So, one way that I use this in my research is sort of illustrated here. So, if you remember the first GIF that I showed you of making the halo, right, where two blobs sort of converged, and then we saw a halo with the central core and the fuzziness out on the corner. So that looked a little bit something like this, just schematically. What I can do is I can make a lot of halos because I do all of these on my computer and I have enough, computer sort of memory and space to do this. So I can set up merging more and more blobs. So I make more and more massive halos, right? Because I just have more and more of the blobs of the same mass. And then once I make those halos, I can analyze precisely how much of the halo is in each of those sort of like preferred shapes, like we just saw with the hydrogen atom, that also exists with fuzzy dark matter. And so one of these preferred shapes corresponds exactly to that core at the center, that little yellow circle, the thing that makes it not like cold dark matter and the reason we like this particle so much, right? So here, what I'm showing you is how much of each of these halos is in this sort of like core-like shape that we like. This is a function of some time. This is time and code units. They only make sense to me in the computer, so don't worry about it too much. But say, one time unit is about 10 giga years, so almost the age of the universe or so. And here what we have is different numbers of blobs that I've collided to make these halos. So we can see that when I collide two halos, my final core is about 60, 70% of the halo. And this is sort of approximately a constant number, right? If you average out these wiggles. When I collide, say, four of the blobs, my final core is about 55, 50% of the halo or so, and so on and so on. So it goes down. Now, this is really interesting because if I'm looking at the stuff that we can see in the universe, right? If I'm looking at all of those beautiful GWST pictures and pictures of galaxies and all of this, I'm looking for things that remind me of fuzzy dark matter. And so, one of the things that I really want to look for is that core because that's a really fundamental prediction. And to look for it, I really want to know how big it is compared to, say, the Milky Way. Like in the Milky Way, how big is this core? Would it extend all the way out to our solar system? Would it extend way farther? Would it extend way closer? That's a good question. And so we can sort of start to answer this question here because we know for each of these halos exactly how big the core is because we can apply the same quantum mechanical principles as we do with the hydrogen atom. And we can sort of plot this relative core size, so how much the mass of the core is compared to the mass of the entire halo, as a function of some parameter psi that we like to use that is just a function of the total energy and mass of the halo. So, two sort of physical numbers that we like to have. So this is actually a figure from a paper of mine that should be coming out in a week or two. So we can sort of see for some 3 different data sets, which don't matter, don't worry about them too much right now, but all of these things sort of have a slope of about 1/3. So, in other words, I use this very small particle behavior, sort of akin to quantum mechanics and akin to the hydrogen atom, to make inferences about these very large dark matter halo effects and astrophysics. And I just think that's really, really neat. And the ability to do this is one of the reasons why I really like working with fuzzy dark matter and why I think it's such a fun idea. So, with that, let's quickly recap. So we've talked about a little bit about what we see in the universe. I say "see" here in quotes because a lot of times we need the assistance of like telescopes or very clever experiments. Or sometimes we can just hear these things in the universe, like gravitational waves, right? So we talked about all of these very small particles that we do see. These particles are sometimes called the standard model of particle physics, by the way. So when we're looking for particles that we've never seen before. We're looking for beyond the standard model particles. We've also talked about big galaxies. I use galaxies here because I'm a cosmologist, so I really like super big things and galaxies and galaxy halos and things like this. But also planets and stars and nebulas and baby stars being born and all of these things. And we've also talked about gravitational waves, which are this really exciting new window into the universe. It's a different way of looking at the universe, right? That we've had only since about 2015, but we're really making great use of as a field, and we're really sort of like hungry to see what else they'll show us. There are also two big things that we don't see in the universe, right? These are dark matter and dark energy. We haven't talked about dark energy a whole lot in this talk because it's not my field of expertise, but that's definitely one of the big weirdnesses in the universe. What we did focus on specifically is dark matter, because that's my field of expertise and I'm quite enamored of it. And so finally, why we talked about why dark matter might be fuzzy. And so fuzzy dark matter is only one idea for what dark matter might be. I've worked on it for a few years now, and I expect to work on it a little bit longer. And I certainly expect to be thinking about dark matter a lot and for the rest of my life. And I can't say that at this point I really sincerely believe that dark matter is fuzzy over any of these other interesting ideas. And I can't even sincerely say that I'm sure that it's one of the ideas that we've come up with and not something totally different that nobody's thought of before. So dark matter is this really, really big question. And for the life of me, I can't tell whether, I'll wake up tomorrow and it'll be solved by one of my colleagues or, someone even coming out of left field with a great idea, or if it'll be, 50 plus more years. So I would say definitely stay tuned in the developments in dark matter, and remember that while fuzzy dark matter is very fun, and I encourage you all to read more about it, that's not necessarily the answer that I'm pushing forward here. I think the answer is to keep asking the big questions. And so with that, I'm going to thank you all. Please enjoy this lovely dark matter simulation courtesy of Ralph at the SLAC National Accelerator Lab. I just found this on the internet, but I think it's really beautiful to look at. And yeah, thank you for your attention.
Thank you so much, Dr. Zagorac, for sharing this look at both the seen and hidden parts of our universe. And congrats on your upcoming paper and your recent doctoral studies completion. That's wonderful. So we are going to check in now with our RASC DDO outreach coordinator, Quinton Wayrich, who has been monitoring the YouTube chat for questions from our viewers. Quinton, over to you.
Hi, thank you so much, Dr. Zagorac. I have not seen any questions from the YouTube chat, but if you don't mind, I've got a couple questions for you of my own, if that'd be okay.
Please, I'd love to hear them.
Okay, so I guess just as like a summing up, you mentioned that the theory of dark matter that you study is fuzzy dark matter, which my understanding is that's an axion theory.
Yep.
And you mentioned that there are a lot of other potential candidates for what dark matter could be. So it's possible that these could be black holes that we haven't accounted for. It's possible that the dark matter may not actually exist, and it's a quirk in how gravity operates, which I believe is modified Newtonian dynamics, correct?
So that's one option. I think so I'm not an expert here. There's sort of like a subtlety in the nomenclature, but I think modified Newtonian dynamics is one version of modified gravity, which is the more general idea of like, hey, what if it's gravity that's wrong? And we should think about how gravity works on these really big scales that we don't experience day to day. So I think that's a subset of modified gravity, if I understand it correctly.
Okay, I see. In addition to those, are there any other like very, I guess, frequently talked about potential candidates for what dark matter could be, and what are they?
Sure. Yeah, that's a great question. So, axion. So, what I'm talking about is one type of axion with a very specific mass range, because basically you need the you need the mass of the particle to be very small to get that bump we like in the center, for it to be fuzzy. That being said, an axion could have almost any mass, I think. There is something called the QCD axion in particular, which is an axion of a particular mass. It's still very light, but nowhere near as light as this. And we like it because it solves another problem in physics, and in fact was first proposed to solve this completely different problem and just happens to be sort of a nice dark matter candidate. So there are experiments around the world, including at Yale, where I did my PhD, that are looking for these QCD axions in particular. For years and years and years, and somewhat still, it was sort of understood, or we all assumed, that dark matter was what's called a WIMP, which is a weakly interacting massive particle. Which is a great acronym if you think about it. So WIMP sort of just this type of particle. They're similar philosophically to axions, but they're sort of different in how they're formed and what their masses are and so forth. They're a little heavier. That would be pretty easy to form in the early universe, and there was sort of hope that we can see evidence of them through CERN for a while. And so for years and years, it was sort of like understood that dark matter was a WIMP, and it was just a matter of time until we found it. And so we never found it, which doesn't mean that it's not true. You can't really prove a negative, right? So dark matter could still be a WIMP, but we got a little tired of sitting around and waiting for WIMPs to show up. So that's certainly still a very popular theory. I think we all just sort of lost our attention span and started looking for other things. So I would say of the two particles, axions and WIMPs are sort of families of particles that are most popular and most well known. Sort of black holes as primordial black holes. So this theoretical type of black hole that comes around not when a star dies and falls in on itself, but rather when one region of space-time sort of falls in on itself and forms what's called a primordial black hole. Those are an option that people got excited about recently. It's looking sort of unlikely that all of dark matter could be made up of primordial black holes just because of certain observations, but it's possible that they exist and that they are part of this missing mass that we're not counting up. So that's the other thing to consider, is that the universe does not necessarily know us a clean and simple solution to dark matter. So maybe they're WIMPs or axions or primordial black holes, or gravity is wrong, or something else. Or maybe there's some subset of these. Maybe they're WIMPs and axions and primordial black holes, and gravity is slightly wrong. So we like to keep things simple, right? The more complicated your theory is, the more it sort of seems like bending over backwards to prove something. But it's possible. So I think the new frontier is sort of considering, or the new train of thought is considering what happens when you have multiple types of dark matter.
Okay, that's a very good answer. I did notice in one of the XKCD graphics, it mentioned sterile neutrinos. Is that a subset of one of the previous theories, or is that a separate theory altogether?
It's kind of a separate theory, which is that neutrino of the sort of standard model particles that we've seen, and so they're not, beyond the, like we know that they're there. Neutrinos are still the most mysterious. They sort of have. We're still sort of trying to nail down exactly what their individual masses are and so on and so forth. And so the idea was like, hey, we don't know that WIMPs exist. We don't know that axions exist, but we really know that neutrinos exist. And we know that neutrinos can't be dark matter because they're moving too quickly and they're maybe not massive enough. But what if there was just like one kind of more massive, slower neutrino that we sort of forgot to account for? Because then maybe that could be dark matter. Because they interact very, very weakly with the stuff around them, right? So many neutrinos are passing through your body at any given moment, and you have no idea, nor would you need to ever worry about that. That was sort of an idea of like, hey, let's think, we heard hoofbeats, let's think horses, not zebras. But it turned out not to really work. There might still be people working on it. I don't know what the most current thing is, but as I remember, that's sort of an idea that never quite took off.
I see. Really interesting. Certainly a lot of research still to do in this field. So Chris Vaughn, who is, I guess, sort of the resident astronomer here at the David Dunlap Observatory, just wanted to comment and say, very interesting. Thank you. And he complimented your sweater. He said, nice sweater.
Thank you.
I believe does it have phases of the moon on it?
It does have phases of the moon on it, yes.
That's lovely. It's a great sweater.
Thank you.
We do have a question from the chat as well, from Maria Lazarev, who asks, do we have any direct experiments testing fuzzy or other dark matter theories, like what we are doing with neutrinos and Higgs bosons?
Sure. Yeah. Great question. So there are no experiments directly testing fuzzy dark matter because the dang particle is just so light that it's sort of like hard to design an experiment of the size that you would need to sort of capture one of these particles. So the best places to look for fuzzy dark matter really are astrophysically, and as an astrophysicist, I like that. That being said, there are plenty of experiments looking for other types of dark matter. So there are plenty of WIMP experiments out there, and there are plenty of experiments looking for axions, like I mentioned. So, for instance, I know at Yale University, so there's an experiment called Haystack, which looks for the aforementioned QCD axion. So it's sort of the same as the particle that I'm putting forward to you. It just has a different mass. It's a little bit heavier, which also means that it sort of like conveniently solves other things. And so the way that this experiment is looking for it, the idea is that, well, it's not that it doesn't ever interact with light. It's that every so often, super rarely, it can sort of like very weakly interact with the magnetic field and produce like one photon, one little bit of light. And so if we look very carefully and for a long time, if we sort of like see this, we know approximately how often this should happen based on certain theories. And so if we look for, 3 times as often as this should happen and we don't see it, then we kind of start to think like, well, probably this isn't the exact mass and this isn't exactly how often these things happen. Let's tweak some parameters and come back. And so what we're doing generally in dark matter studies is sort of excluding what's called parameter space. So, I can run some experiments and say, well, a mass of 10 to the minus 23 electron volts doesn't really work because of it doesn't match predictions from Milky Way. Let's try 10 to the minus 22 instead. Or, like 700 electron volts doesn't really work. Let's try 800. Or like 700 electron volts at like a certain coupling constant, which basically means that it should interact on average once every year, doesn't really work. What if we assumed that it interacted once 2 years? So we sort of chip away at this like very long graphic that I showed you of all of these different masses and theories and ideas. And so it's sort of, I don't know. I think it's sort of the equivalent of trying to sort of dig out the truth from like the heart of a mountain, but you only have like a toothpick or something. So we're all very diligently sort of chipping away with our toothpicks, hoping to, hoping to strike, hoping to find knowledge somewhere in the center. So there are plenty of experiments running.
Well, I mean, eventually we're bound to make a breakthrough, but who knows where it's going to come from, right?
Yeah, that's sort of sometimes I get asked if I feel pessimistic about that, but I think it's kind of like I don't even feel pessimistic. I feel unable to make a prediction because from where I'm sitting, it truly could be tomorrow, or it could be 100 years from now, or maybe not even then. So I think a lot of sort of like luck and clever ideas play a lot of role in this, and sort of new ideas, right? So I'm always trying to sort of like I'm always trying to listen to sort of folks that think a little bit differently than me about these things because maybe if you get, the right 2 people in a room talking, we can think of sort of like a new way to approach this question. And I think that's actually exciting. I don't think that's depressing at all. I think it's exciting that we don't know everything about the universe still.
I agree. I mean, it's always great to have more questions to ask, more horizons to expand on.
Yeah. Yeah,
Maria,
absolutely.
so Maria has thanked you for your answer. It was a very good answer. That seems to conclude all the questions from the chat. So thank you very much.
Thank you, everyone.
Thanks, Quinton, for relaying those great audience questions. And thank you so much, Dr. Zagorac, for your very thoughtful and thorough answers. We do have a little more on our program for you tonight. Since this is a DDO online event, we do have a tour of the DDO prepared for you as a short video tour. We will come back after the tour to answer any questions you might have about the telescope and the DDO facility.
Hello and welcome to the David Dunlap Observatory. Behind me is Canada's largest optical telescope. My name is Denise Chilton and I am a rascal. a member of the Royal Astronomical Society of Canada, Toronto Centre. It is my pleasure to be an operator for this telescope, and tonight I'm going to give you an inside look at this telescope and how it works. But first, let's think about the history of this scope. This facility opened in 1935. Originally, it was a research telescope for the University of Toronto. It was named in memory of David Dunlap, who had thought that he was going to provide some funding for the construction of this scope, but his unfortunate death prior to that funding being secured put the future of the scope in jeopardy. It's very lucky that his widow, Jessie Dunlap, came forward to donate the funds for this facility. The telescope was built by Grubb Parsons in England, in Newcastle on Tyne, in 1932 and 1933. It was shipped across the Atlantic in pieces after being completely built and assembled and then disassembled in England. It was shipped here and rebuilt on this site, and it opened in 1935. It was in use as a research telescope for many years, but unfortunately, due to light pollution and the availability of bigger and better research telescope facilities, the University of Toronto closed this telescope in 2008, and the property was eventually sold to the city of Richmond Hill. The good news is that the telescope is now open for public tours. Unfortunately, with COVID, we can't have people in the building, but tonight it will be my pleasure to show you how this telescope works. So how does a telescope work? Well, a telescope points outside at the night sky. Light flows down the optical tube, light from moon or stars or planets or dark sky objects, and it's collected by the great big mirror behind me. This is the primary mirror in the telescope. In this case, this one is 74 inches across, or 1.88 meters. You can probably see my reflection back there behind me, and it's this diameter that makes this telescope so powerful at collecting light and in being able to see very distant objects. When this facility opened in 1935, this became Canada's largest optical telescope, taking that record from the Dominion Astrophysical Observatory in Victoria, British Columbia. Their mirror is only 72 inches in diameter. Rumor has it that when Dr. Clarence Chant, who commissioned this telescope, placed the order for this mirror, he asked specifically for it to be 2 inches bigger than the Dominion Astrophysical Observatory's telescope mirror, so that he could have the record of the largest telescope in Canada. When this opened, it was also the second largest telescope in the world. No longer the case, of course, as much larger optical telescopes have been created since then. To get back to how a telescope works, light flows in from the night sky outside. It is collected by this great big primary mirror and bounced back in that direction toward you. I'm not sure if you can see this contraption at the top end of the telescope here. This is the secondary mirror attached to these vanes. The secondary mirror collects the light from this primary mirror and sends it back down the telescope to the hole in the very center of the mirror. This hole leads to an eyepiece down below, and that's where you, if you were here, could come and look through the telescope and see distant planets, distant stars, or dark sky objects. You might have noticed that the sun rises in the east and sets in the west. If you were to stay up all night, you might notice that all of the objects in the night sky do the same. the moon, the stars, the planets, and more. This is because the Earth is rotating. But what this means is that the telescope needs to be able to lock on to night sky objects and then track them across the sky as the Earth rotates. So we have some controls over here that allow us to lock onto our targets. Every object in the night sky has a set of coordinates. We call these coordinates right ascension for east to west and declination for north to south. These are the same as latitude and longitude coordinates for objects on Earth. Let me show you how our controllers work. This is our declination controller. It helps the telescope move north to south. Let's watch how that works. As the telescope is moving north, we can see the coordinates in the counterweight on the other side of the telescope, so we know exactly where it's pointed. Now that we have our declination coordinates locked in, north to south, we're going to lock in our right ascension coordinates, east to west. We use this wheel to do that. First, we unlock the telescope. And then we can turn the wheel, and our coordinate system is up here on the setting circle so that you can see where the telescope is pointing exactly. And we turn the wheel until it's pointing in the right direction. Once the telescope is pointed in the correct direction, we need to lock it in place again so that it doesn't swing around. But you might have noticed that the telescope is no longer pointing at the open sky. Instead, it's pointing at the inside of the dome. So we need to rotate the dome roof to bring the open window in front of the end of the telescope. The dome weighs 80 tons. It rotates on a set of 24 train wheels connected to a cable and pulley system powered by a motor downstairs. Once the open shutters are in position, we're ready to start observing the night sky. Just up this ladder, we can find our way to the eyepiece. I wonder what I'll see tonight. Thanks for joining us for this virtual tour of the David Dunlap Observatory. We hope to see you here in person as soon as we're able to reopen the facility for public tours. Until then, wishing you clear skies.
I hope you enjoyed that tour of the facility and that this glimpse inspires you to visit us here at the DDO very soon to learn more about the facility and its rich research history. The facility has now fully reopened to the public, and we are looking forward to hosting some in-person events here very soon. If this tour isn't enough to pique your interest in visiting us here at the DDO, let's take a quick look now at a view through the 1.88 meter or 74-inch telescope here at the observatory. Unfortunately, tonight is clouded out, but we do have a video that we've already recorded for you of Mars coming up on your screen now. This was taken a couple of years ago, and you can see some of the great planetary features in this video. You can see the Syrtis Major Planum, that's that dark spike sort of pointing to the 8 o'clock position. The dark color comes from exposed volcanic rock. The Hellas Basin is the lighter area above Syrtis Major. That's the largest recognizable impact basin on the planet, and it's about 7,000 kilometers across. The South Pole is slightly white, and that's at the 2 o'clock position. It's a little difficult to see, but if you concentrate, you'll see that there is a little bit of a white patch right there. And below the Syrtis Major area, that dark spike again, featured an area that was featured in the film and the book, The Martian, is the Arabia Terra. And that's where Mark Watney in that film got stuck in a dust storm. So this video was processed and enhanced a bit by one of our RASC members, Claudio Oriani, and it's a little clearer than what we might normally see through the big telescope in real time. Now is a wonderful time to observe Mars. It was at opposition earlier this week, meaning that it rises as the sun sets. It's up all night long, and it sets as the sun rises in the morning. So it's a great time to observe Mars. You can see it in a backyard telescope. You can see it, of course, with your own eyes. It's that beautiful, bright, red, shining star. It's not a star, it's a planet, right up there in the night sky. So let's hope for some clearer skies. Unfortunately, tonight was cloudy here. Otherwise, we would have brought you a live view of Mars. So now let's go back over to our outreach coordinator, Quinton Wayrich, for any questions about the David Dunlap Observatory. Quinton, have people been chatting over in the YouTube chat?
Thank you so much, Denise. There do not appear to be any questions from the YouTube chat about the observatory right now.
Okay, great. Thank you so much, Quinton. On behalf of the Royal Astronomical Society of Canada Toronto Centre and the RASC DDO Committee, I'd really love to thank Dr. Luna Zagorac once again for this amazing look at the fuzzy things out there in our universe. Thanks also to our technical support team, Andrew Reed and Betty Reed, and of course to Quinton Wayrich for fielding the questions from our YouTube audience. Finally, a special thank you to all of our viewers for joining us this evening and for your questions. This talk is the last event of our 2022 season of astronomy events at the David Dunlap Observatory, offered through the partnership of the Royal Astronomical Society of Canada Toronto Centre and the City of Richmond Hill. However, we do have a wonderful lineup of events coming in January and running all of next year. We will be beginning with an in-person astronomy speakers night on January 6th. Tickets are available through the Active RH Richmond Hill system. That's followed by an in-person planetarium day on January 8th. This is where our senior astronomer here at the DDO, Chris Vaughn, brings his inflatable planetarium to the facility, and everybody huddles in and gets a wonderful tour of the night sky right in the middle of the afternoon. We have a virtual Up in the Sky event coming to you on January 28th. At this point, all of our RASC members get out their telescopes and their cameras, and they point those at different targets, and we share them with you along with some information about the cosmos, the solar system, and whatever we're looking at. And we do have a virtual Sunday sun gazing event also coming up on January 29th. Now, at those events, we have our RASC members point their telescopes at the sun, of course, with special filters for solar observing safety. And we'll bring you all kinds of interesting facts and information about our closest star, as well as hopefully live views of the sun. All of these events and more are posted on our website. That's rascto.ca. So please do have a look there for more details. We are hoping that tonight's event has you excited about getting out there and observing the skies for yourself. So we would like to end this evening with a quick video on getting started in astronomy. Wishing you a wonderful night and clear skies. A question we're often asked is, how do I get started in astronomy? It's a really great hobby, especially in this COVID context. It gets you outside for fresh air, you don't need to do it in a group, and there are tons of free resources online. So here's a quick guide to getting started in astronomy. Step 1 is to learn the sky. This really is essential, as it's important to be able to orient yourself and know what you're looking at. There are lots of resources to help you with this. If you prefer books, I can recommend Night Watch by Terence Dickinson or The Beginner's Observing Guide by Leo Enright. Or if you'd like to print out some star maps and star finders, There is the star finder from the Royal Astronomical Society of Canada. That's a printable star finder that you can take out with you under the night sky, or you can print sky maps and sky atlases from skymaps.com. If you're a little more tech savvy and you prefer programs and apps, I recommend Stellarium. This is free planetarium software you can install on your home computer, or Sky Safari. This is an excellent app for your phone. Once you've got your bearings, step 2 is to start observing. That's right, just head out under the night sky and look up. You don't need any special equipment, just your eyes. With your eyes, you can see things like constellations and asterisms. These are the formal and informal patterns that stars make in the night sky. You can see planets like Mars and several other planets as well. You can see the moon and observe its different phases as it moves across the sky. You can see meteor showers, comets, and even one galaxy that's bright enough to see with your naked eyes in a very dark sky area. Maybe you're inspired to look for more than what you can just see with your naked eyes. So step 3 is it's time to start collecting some gear. Now, you might be surprised that you may already have some of the things you need lying around the house. If you have a pair of binoculars, you can point those at the stars. If you don't, they're a small investment with a lot of benefits. With binoculars, you can see details like craters on the moon, or the phases of Venus and the moons of the planet Jupiter. You can even see smaller, fainter asterisms and double stars. Remember, one of our famous astronomers in history, Galileo, started out by using a telescope that didn't have much more magnifying power than an average pair of binoculars. His contributions to astronomy are remarkable, and you can see a lot through your binoculars too. If you're ready to get a little more serious about your astronomy hobby, you might consider investing in a telescope. A small amateur telescope is a big investment, but with more magnification possible, you can see more detail on the surface of planets, the moon's craters. You can see many double stars, some galaxies, and nebulas, and other deep sky objects. I recommend joining the Royal Astronomical Society of Canada to participate in the telescope loan program if you're interested in buying a telescope. You'll have an opportunity to try out many different scopes and determine which one is best for you. And this brings us to step 4, connect to a community. You can find information about the Royal Astronomical Society of Canada Toronto Centre online at rascto.ca. And through RASC, you can learn about upcoming astronomy events, you can find more astronomy resources, and you can become a member of the club for additional benefits, like that telescope loan program I mentioned. I hope this guide has helped you to feel confident in getting started in astronomy. Enjoy those clear night skies.